Good morning. Myself Suyesh Pandey. My group mates Aditya, Shiv Kumar, Akshat Goyal, Akhil Vish, and Durgesh Pandey are going to talk about active suspension system. Firstly, we need to know the requirement of a suspension system, or rather the function the suspension system needs to perform. Right. So the main task of a suspension system is to show that is to isolate the driver from the various shocks that the road provides, and also to maintain the tire contact between the road and the vehicle. So when we talk about the suspension system, it is a compromise between the comfort and the riding stability. So when we talk about a suspension system in cars such as a sports car or a luxury car, they are very different. A luxury car needs to make aggressive turns, for which the suspension system needs to be hard, so that the oscillation or the vibrations are not felt that much, so the stability is maintained. Whereas in luxury cars, we don't need that kind of driving, so that the suspension system can be soft. A good design of a passive suspension system can work up to some extent to eliminate this compromise, but cannot completely do that. And this is where the role of an active suspension system comes into play. So the basic working of a fully active suspension system needs to completely eliminate this compromise, right? So how does it do that? It senses the shocks that are faced by the car body and which are there from the road, and somehow actively provide the forces which will counter these shocks, right? So we are going to look at a diagram now, right? So this is, for example, a road, and the stiffness of a tire is represented by KT. The mass of the vehicle is shown here, and the car body is shown here. The suspension system's stiffness and the dampness is again shown here. There is a sensor on the car body which senses the various vibrations or the accelerations which the car body faces, which ideally should not be there, right? So when the sensor senses a displacement or an acceleration of the car body, it sends that signal to the controller. The controller then determines the kind of forces or the kind of actions it needs to send to the transducer, so that an active force can be generated which will be opposite to that acceleration and the displacement hence required. So it then sends it back to the transducer, which which converts the digital signal to the physical property and changes the system such that the vibration and the acceleration can be eliminated and the shocks can be damped.
Basically a proportional integral derivative controller. The main use of the PID controller is to eliminate the errors or displacements, and the other main use of the PID controller is to eliminate the need for continuous operator attention. And there are in PID controller there are various functions or actions. The first one is integral action, second one is derivative action. So the first action is integral action. So whenever there is a offset in an active suspension system, so it will increase the controller gain. So which will result in a loop unstable condition. So to eliminate the loop unstable condition, we are using integral gain system, which will eliminate the offset. And second one is derivative action. So with derivative action, the controller output, it will be proportional to the change of measurement of the whole operation or error. So whenever there is a load or a set point change occurs, so then the controller gain, it will cause it to move in the wrong direction. So and the another use of the PID controller, it is used to provide a control loop for the active suspension system.
So what we are going to see now is the hydraulic active suspension system. The main parts of the hydraulic active suspension system are the pressurized hydraulic fluid source, a pressure relief valve to control the pressure of hydraulic fluid, a directional valve control, hydraulic cylinder to convert the hydraulic pressure into force to be transmitted between the sprung and the unsprung mass. So this is the diagram where the vibrations from the rod are input into the unsprung mass, that is the axle. From the unsprung mass, it is going to the hydraulic piston. This hydraulic piston sends the vibrations to unsprung mass as well as the sprung mass, that is the chassis. From the chassis, the sensors, that is accelerometer, senses this and sends it to the PID control, which converts the current and sends it to the scaling amplifier. This amplifier amplifies the signals of the vibrations and sends it to the pressure relief valve. This pressure relief valve is controlled by the hydraulic power pack, and the pressure relief valve sends the fluid flow into the hydraulic piston. From the hydraulic piston, the anti-vibrations are sent back to the wheels, which dampen the vibrations. Now in this we see that this is the actual displacement which is going to this piston, which moves up and down, and this control of this piston is measured by the anti-vibrations from this piston X6 that sends back to this and controls it.
So now I'm going to tell you about the controller design. So this is the mathematical formula which we use for the overall calculation. So where the UC is the current input from the controller, and Kp, it is the value of proportional gain, where Td and Ti they are derivative time and integral time with respect to controller design. So what is the tuning of controller? It is basically the process of selecting controller parameters for designing a specific condition. So this condition is known as tuning of controller. So it is basically complete design based on the value of Kp, which is known as proportional gain. So there is a one rule which is known as Ziegler-Nicholas rule. So it will give us the value of Kd, Kp, Ti and Td, based on which we can get the result which are completely stable operation, or that will give a most accurate value in with respect to other conditions. Now these are the graphs which we got from the result. So this graph is for the closed loop condition for active suspension system, and it is for sustained oscillations. So the graph will be is made between car body displacement and time. So the graph is start from at 0 point, and the other graph it is for closed loop condition for active suspension system, but it is for non-sustained oscillation. So here this is also made between the car displacement and time.
Now we have done a simulation on a quarter car model of a car. So these are the following parameters which we use. MB is the weight of the quarter car model, which is equal to 300 kg. KT is the tire stiffness, which is equal to 1,90,000 Newton per meter. MUS is the mass of the unsprung system, which is equal to 60 kg. Beta is the frequency of the damping of the suspension system. Ka is the stiffness of the spring in the suspension system. PS is the pressure in the hydraulic pressure in the suspension, which is equal to 10.55 megapascal. Consider ZR as a function which is used to simulate the displacement of a vehicle. Now this is the quarter car model of a car, where the axle and the tire make up the unsprung mass, and the vehicle body makes up the sprung mass, which is supported by a spring and a damper. This part is the road profile. Now after simulation in MATLAB, we get the following graph where the spike represents the bump in the road of the single bump. Now we will consider the following graphs where the difference between the displacements of passive and active suspension system is there. The graph on my left, it represents the displacement of the car body of a passive suspension system, and on my right is the displacement of an active suspension system. You can clearly see that the vibrations are being damped out very quickly in active suspension system, whereas a lot of time is being taken for to disperse the vibration in passive suspension system. Also, there are more number of vibrations and in passive suspension system when we compare it to active suspension system. Now we will see the suspension travel of an active suspension system. The y-axis represents the suspension travel, which is with respect to time in the x-axis. Now we can see that the suspension travel is very less, only about 0.3 mm, 0.03 meter, which is being traveled by the suspension system. Now we will see the sprung mass displacement versus time. Now the solid line represents the displacement of an active suspension system, The dotted line represents the displacement of a passive suspension system, and this is the road profile. We can see that there is a bump, and the passive suspension system is reacting to it very differently when compared to the active suspension system. There is more displacement, and there is more time is being taken to disperse out the vibrations when we compare it to the active suspension system.
As my friend Aditya explained about the simulation of bumpy road, I will be explaining the simulation of a pothole in the MATLAB. So we took a function of ZR again with the constant pothole for 1 second with a displacement of 0.05 meters. This graph shows, the straight line in the graph shows the road profile for the time period, where the dotted line shows the performance of a passive suspension system in the pothole. It can be seen that the displacement that the passive suspension travels is quite high with respect to the active suspension system, wherein the active suspension system hardly goes to 0.01 meters. This is the graph simulated after the suspension travel versus time, that was the sprung mass displacement. In this graph, the time period required for the active suspension system to damp the frequencies and displacement is almost half of that of the passive suspension system, and also the displacement here in the passive suspension system is around 6 centimeter, whereas in the active suspension it's also less than 1 centimeter. This proves that it's very efficient in damping the. This is the graph of a random road. In a random road, I mean, in the simulated time period, it covers the straight patch, bump, and also the potholes. The function ZR, A sin theta, omega s minus phi. In this graph, you can see that the performance of a passive suspension system over a larger time period, including all the different road profiles, is not very effective as compared to active suspension system. Passive suspension system only performs good in some of the regions, whereas active suspension system can be seen that it efficiently damps almost all the vibrations over the larger time period, whereas the passive suspension system still stores some travel. This is the suspension travel of the system, wherein the passive spring damps the road profile, wherein the spring travel is quite high with respect to the active suspension system. In this, what happens, the damper and the spring, how they work is like they take in the forces from the road, and the spring oscillates to damp the forces. That oscillation is quite high of the passive system, whereas it's very negligible in compared to active suspension, thus isolating the vehicle from the road.
Now we'll summarize how we have seen what we have seen throughout the presentation. We have simulated the profile of a bumpy road, a pothole, and as well as a random road. So when we see the results of a suspension travel, we see a major difference between passive system and an active system. In a bumpy road, the difference of reduction is approximately 72% or 71%. And when we see for potholes or a random road, it goes up to 89 and as well as 88%. So it automatically proves how efficient not only the active system is in decreasing the amount of vibrations and displacement, but also, as we saw in the various graphs, that active suspension system diminishes and damps the various vibrations and accelerations in a very small time period. Now to conclude, we saw the various simulated results that how an active suspension system with PID controller works very efficiently when we compare it to the passive suspension system. The comparison then shows the performance of an active suspension system very efficiently isolates the driver and the passengers from the various shocks of the road, irrespective whether it is on a pothole, whether it is on a bumpy road, or any random road for any given stretch of time. We have tried to include the various parameters for the design. When we talked about the PID controller and the hydraulic system, we talked about the various components and as well as the various parameters which control these components. Thank you.